Note to the production team. Just as I finished up that last part, I recognized that I had made a slight mistake when I went to the new fresh page. Didn't like where that was heading, so I stopped the recording. So now you'll just need to patch these two. All you have to do is cut out the last little part where I started to write down this part here. Okay, so we're going to get ready to begin. I'll give you a brief pause so it's easy to figure out where the blank is. Okay, so let's go back now to our rate of return example in a numerical standpoint. And remember, we said that, hey, this rate of return was normally distributed with mean of 10 and standard deviation of 15. And we also talked about that when we define z as being equal to x minus its mean divided by its standard deviation, that z was also going to be normal, but with mean 0 and standard deviation of 1. And so we were going to go after, well, what's the probability that we have a loss in any one year? So that's the probability that x is less than 0, a negative return. Right, so that was our loss in a year. Right, well, we can go back and substitute in the value for 0 in for x, and so this is also asking us then, what's the probability that z is less than minus 0.667. How did I get that 0.667? Well, I plugged in the 0, plugged in 10 for the mean, and 15, keeping track of signs for the mean. Right, so 0 minus 10 divided by 15 gave us the minus 0.667. And we're going to not use MathCAD to symbolically evaluate this, although you probably could use it to numerically evaluate this. We could also go use Excel and all kinds of tools. I'm going to show you how to use the standard normal tables that are provided to you in Montgomery and Runger, because that's what will be authorized aid on your exam. And that's back in the appendix in table 3. And I shall freeze the frame here for a second while I go and pull that out. So now here we are on page 708 of the Montgomery and Runger text, the standard normal table, and notice that's the cumulative standard normal distribution. Standard is key, cumulative is key. The cumulative says that it's going to give us probabilities or areas to the left of our little z value, right? And there's your expression up here that verifies also what they're doing. Sometimes they'll give you both, sometimes they'll only give you one. One key thing to keep track of is that sometimes they don't give you this view, they instead give you the z on the other side, and they're going to give you the area that's out here. That's not the cumulative, that's 1 minus the cumulative. But we'll talk in a moment about how you could actually use this to make the tables, instead of 2 pages, just 1 page. And that's of course the reason why a lot of publishers do it that way. For us, we're going to be looking at minus 0.667 for the z value. And the way you read this table is that you've got the stem of the z over here, and you've got the leaf going out in this direction. So if my number was minus 0.397, I would take minus 0.39 and I would come over to 0.07. So the column heading and the row heading are added together to get you your z value. And the number that's in the table then is the tail area that's to the left of z, right? So that says, wow, there's a really small amount of area to the left of minus 3.97 on the standard normal distribution, 0.000036. If you want percent, of course you multiply this number by 100 to get percent. We're at minus 0.667, and notice our resolution here is only to the nearest hundredth. If you wanted to, these are so tightly packed that you could do linear interpolation. I don't know anybody that does that. They just say, okay, this is good enough. I'll round to the nearest hundredth. So we're at minus 0.67. So we'll be in that particular column, and now I'll slide the book up so that we can get to the minus 0.6 right down here at the bottom of the screen. So let me move that up a little bit more, and there you see that the number we end up with is 0.2514. Go ahead and jot that down on a sheet of paper, because we're going to come back to that here in just a second. Right, because before we go, I want you to see the right hand side of the table. Right, go to the facing page, and it's really nice with this particular publisher that they put these on facing pages instead of the other side. It's quite annoying when they put them on opposite sides of the paper instead of the facing. So here we still have the cumulative distribution, all the area to the left of z. So note, if we go to a positive 0.67, here's our 0.07, and go to 0.6, see they shade these rows to make it easier. Notice you got 0.748571. If you were to add the 0.748571 to the number that we found to the left of negative 0.67, you'd get exactly 1. Try it. See. Right? Because remember, it's a symmetric distribution. So whatever was to the left of 0.67, whatever's to the left of minus 0.67 is to the right of a plus 0.67. Right. Let me rephrase all that. Maybe that's sort of confusing. Right? Remember, this tail area is just 1 minus all of this area. Right? Symmetric distribution, so if we have a 0.67 here, bounce it over to negative 0.67, this tail area whoop, gets flipped over. Right? So when we found the 0.2541, we were actually finding the 0.25 over here as well. Add those two together, total area under the curve has to be 1. Right? So the answer to the question of what's the likelihood of loss in any one year is going to be, well, we're going to go to the standard normal table, evaluated at minus 0.667, and what we just discovered was that that value is 0.2514, not 41, but 14, or about 25% of the time. Right, so that's in any one given year. We have 25 or 1/4 chance that we're going to end up with a loss. Whether that's within your threshold of risk or not is up to you to decide. But here's another interesting question. What if we weren't looking at a 1-year investment? What if we wanted to know about a 30-year investment? Say, what's the expected value of a return after 30 years? Or what's the variance on that return after 30 years? Because remember, we learned how important variance is. Or another question to ask is, what's my probability of loss after 30 years? Right? Obviously here, this is a long-term investment. Maybe it's a retirement investment, that sort of thing. All interesting questions, and we're not going to answer it, but we're going to set it up slightly. And one of the ways that you might do that is you might come back and say, okay, let's let y be the return on investment after 30 years. And we could think about that then as nothing more than the sum of all of the returns over those 30 years. So we could start asking the question then up here, okay, this is just the expected value of y, this is the variance of y, and this is the probability that y is less than 0. All well, fine and good. The problem, though, is that y is a function of random variables, of which right now we don't necessarily know what happens from year to year. And that's going to be the big question, is how are these related? Are they identically distributed? Are they correlated? Are they functionally dependent on each other? Therefore, they'd be statistically dependent on each other. How do we deal with all that? That's a real interesting question. But at the very least, we can say, well, y is the sum of a whole bunch of things that have happened over the 30 years. And so by the central limit theorem, we should expect that y is going to be normally distributed. And it's going to have some sort of mean, and it's going to have some sort of standard deviation. But evaluating what that standard deviation and mean is going to be is something for another day. Something that will happen, that we'll come back to and return at some point in our exploration this semester.